Hey, how's it going? I'm going to do a small, hopefully, tutorial on how to do the BOE-Bot by Parralax Incorporated. It's about 150 bucks, but it's a really good kit. It'll get you started on how to program robots to do different things. This model basically is just for travel over land. It's got two continuous servo motors that turn the wheels. You can get different modifications so that you can maybe get some treads if you want to go over rougher terrain, but I don't know how they would outfit the maybe different a quadruped, for example, on the continuous rotation servo motors that they have right now. So this is it right here. His name is BMO, not very creative, I know, but since it's the BOE-Bot, I figured that BMO is pretty close, and actually, it was Bebo originally, but Panina didn't really like that name, so I decided to change it. But yeah, I mean, it's pretty simple. First things first, though, we'll go over some of the major areas that you're going to be programming with this kit. So first of all, you have the microcontroller here. This is the basic stamp 2 microcontroller. There's version 1 and there's some other versions too, but it really matters which one that you have so that you know how to program with it. You're going to use PBASIC, which is a derivative of BASIC, to program this microcontroller. It's really simple. If you've ever used BASIC before, even if you haven't, it's probably one of the easiest languages to learn. I mean, I've dabbled in a few different languages, but this one is definitely one of the easier ones to understand, especially if you might be more of a visual type person, maybe the kind of person that has to actually physically do something in order to get it, then this is going to be one of the types of things that you might want to do. A little aside, I guess, with software programming in general, since it's a little bit more abstract, if you've ever dabbled in that sort of thing, you might not have gotten it or gotten a whole lot of satisfaction out of it. But one of the things I think that's great about robotics is that it combines software, hardware, engineering, physics, all those things together to come up with a single product. So yeah, BASIC is going to program your microcontroller to basically output zeros and ones, to apply voltage in certain places or not to. That's what it boils down to. It's all just binary. So yeah, you have your microcontroller here. This location, they're referred to as the X4 and the X5 ports, I guess you would say. Those are going to connect to your servo motors, which are the wheels. You don't need to program them any differently from the rest of the pins for the microcontroller because they're going to, well, that's not necessarily true. If you're going to use the specific pins, then you're going to want to do ins and outs of those specific pins, but you're going to want to do pulses out for the locations that whatever your servo motors are connected to. Mine are connected to 12 and 13, which I don't know if you can see. But they're on the top over here. Oh god, this is so hard. Over here, it'll actually say 12 and 13. So whenever you send pulses out to those locations, then it's going to put them there. What else? So, yeah, that's pretty easy. One of the distinctions, though, that I'm just now noticing is that the microcontroller does have a pin 13 and a pin 12, but it won't output pulse out signals to those if you just use the pulse out command. It automatically knows where to send it to. So yeah, you have that. This is called your breadboard, or your prototyping area, as it's sometimes referred to in the text. This is where you're going to hook up all your actual hardware circuitry to make your different sensor sets and things like that. Basically whatever else you want to do. So each of the pins in the black right here are going to be connected to one of the outputs for the microcontroller. So if you wanted to output, for example, a 1 signal or a high signal to the first pin, which is connected to an LED here. I have my resistor first, which you should have because that's how I blew out an LED. I didn't have a sensor before I sent a high signal to the LED, and it fucking exploded in my face, and it was scary and it was loud. So you want to make sure you know what you're doing and always use resistors in your circuits if it's necessary. Anyways, yeah, so connected to pin 1 I have a resistor which is connected to an LED, and that's just basically going to light up. To complete the entire circuit though, of course, you need to have your negative and your positive side all connected in a loop. And so you have to hook up, like, pin 1 resistor is going to go to this second row right here because the first one is pin 0, and that's going to be connected to my negative side, and it's going to go to the next side, and then I have a wire which you can actually see is going to run right next to it. Oh gosh. Right here, and then, I mean, the entire circuit is kind of confusing, but it's connected into where the piezo speaker is, which makes noises, but then that's going to all be connected back to VSS to complete the circuit. So I hope that that's not too confusing. I think I might have fudged the explanation, but you need to have a circuit as a complete circle of voltage, or else it's not going to do anything. So yeah, that's how they all work. Each of the pins does something different because I have something different connected to it. You can arrange it however you want. It's actually best to hack at this point and change things around so that you kind of know what everything does and how it works, because if you can't tinker with it, then you don't really understand what's going on with it. You know, you want to try different prototypes of accomplishing different tasks or performing different functions so that you yourself as a learner can understand what can and can't be done with your code for you to, like, actually have something that's going to be successful. So I highly suggest that you do that. That's pretty much like the basics of the board. We'll go into the actual file itself that I have written already called Advanced Whiskers, and that's going to be like navigating through tactile navigation, as I've, you know, kind of alluded to on my Facebook post if you've seen any of those. It's going to basically read the inputs from these two whiskers. Okay, so like I was talking about earlier, how you have to have a complete circuit in order for the microcontroller to, like, you know what's going on and be able to give signals somewhere. Whenever a whisker is not pressed, it's going to complete a circuit with a 1. So, you know, you output a signal from the microcontroller, that's a 1. It goes all the way through on pins. It's going to be pins 7 and 5 for this program. But it's connected to the resistor. The resistor goes into one of the switches, which is one of these things right here. Whenever it's not pressed, it's a complete circuit, and the voltage is like, zzz, well, the current rather, zzz, going through. But as soon as you press one of the whiskers, it interrupts that circuit, and that's going to send a 0 to the microcontroller. So that's how the microcontroller is going to know that something has been pressed. So that works for both the left and the right hand sides. That is the only sensor set that this particular model has. I wanted to describe that and show that before I move on to the infrared navigation and the photoreceptor navigation too. You know, because I'm gonna break down this prototype area, so it's not gonna be there anymore. But if you want to know what's going on with this especially, then, you know, I can show you now, because it's not gonna be here, and I don't feel like building it up again because it's pretty rudimentary. One of the things that I noticed for this particular sensor arrangement is that the bot is going to fall over a lot, because as you can see, I mean, just use your brain, right? Like, all it can detect is if something is here. So if there's a wall that's right here in the corner, it's not going to detect it, and it's just going to keep going. I'll go into why that happens in the code itself, but yeah, it's just kind of crappy. I'm not saying like it's the worst thing ever or whatever. Like, I would never use tactile navigation because I know that there are some instances where it would be useful and successful, but just for navigating around the real world, it's not really all that useful if you have just two whiskers in the front of your robot telling you that it's hitting stuff. So anyways, let let me go into the Advanced Whiskers program. It's really simple code. It's not really all that complicated. There is one part, the decision making for if there's alternate touches on each of the whiskers from the 5 and 7 inputs that tells it that it's stuck in a corner, which is the only like decision making or artificial intelligence code sequence that's going to be in this program. I'll try and go over that kind of slowly so that you can understand what's going on. Then I also have my pulse width RPM chart that I can show you how I calibrated the servo motors to go in a straight line, because it took like an hour and a half to get these values. And to be completely honest, this is only for one side. I didn't even do the other side because I was like, But anyways, yeah, so here we go. All right. The very first line of codes that you want to have for most of the programs that you're going to write, whether they be in PBASIC or any other programming language, most, not all, you're going to want to like declare your variables, and you're going to want to tell the computer what they are specifically, as far as, in this case, sizes that need to be allocated inside of the EEPROM module, which is, it serves the same function here, kind of like as RAM would in a way, but it's more ROM. It's going to keep whatever values are in there for an extended period of time, like even after the power's been cut to the rest of the circuit. Where RAM, on the other hand, as soon as power's disconnected, it's gone. So yeah, I won't get into the differences between RAM and ROM. I don't think it's either here nor there, or neither, or whatever. Anyways, the first variable I have is called pulse count. It's a variable, and I need 8 bits of space, otherwise known as 1 byte of space, for memory allocation. The counter is a variable. I only need a nibble full of space, which if you've never heard that before, it's just half of a byte. Okay, so you have a bit, a nibble, and a byte. A lot of people know about the byte and the bit, but not the nibble. Nibble's half a byte and 4 times as big as a bit. So a byte is 8 bits, a nibble is 4 bits, and a bit is 1 bit. Anyways, yeah, I only need to count up to 4, so I'm okay with having just a nibble for that one. Old 7 is going to be the old value of the input to the 7 switch that the microcontroller reads, and I only need it to be a 0 or 1 because it's either pressed or it's not pressed. Old 5 variable, and I just need a bit for that one too, either a 0 or 1. So now that I have my variables introduced to the microcontroller, then I need to assign them an initial value. For the counter, I just want it to equal 1. Old 7 is going to be 0, and old 5 is going to be 1. The book says that you should set these to different values at the very beginning, and I'm not really sure how the program would be much different if I didn't have it like that. I don't know. I mean, I didn't really mess with this one too much. I was just like, okay. Like, I tried to change the values to 1 and 1, and then, like, I massacred the rest of the code, and, like, it didn't work, so I was like, screw it. For right now, I'm just gonna set it the way that it told me to. So anyways, those are the old values. Okay, so the very first thing that I want to do is to debug out, which means to just display on the screen whisker navigation. The next line is CR, which stands for carriage return, which means that I'm going to go to the next line of the debug terminal. So I'll show you what the debug terminal looks like so that you can kind of know what's going on. If you heard that beeping, that's my robot. If you didn't, don't worry about it. It's not a big deal. Okay, so I'm going to load the code into the microcontroller, and this is the debug terminal. So like I said, God damn, I hate it when I do that. So I don't know how to make that other one come to the front. I'm so dumb. Here, I'll just do it again. That's not what I'm looking for. So dumb. Alright, anyways, I'm not going to click because then it'll go away. Okay, debug whisker navigation, that's going to be on XY position 0, 0, which is going to come into play a little bit later. carriage return, so then I wanted to just say, okay, space after that, like enter after that, whatever. Freak out 9, 600, 1200, and 9, 600, 2000, and freak out 9, 600, 2600. Those are frequency out signals sent to pin 9 of the microcontroller for 600 milliseconds each at 1200, 2000, and 2600 hertz respectively. If you know what 2600 hertz is, you are a freak. And if you know what a freak is, then you are a hacker. Okay, so anyways, yeah, so freak out is going to go to pin number 9, which is this black wire right here. Okay, oh gosh, right here. It's going to be connected to the positive side of my piezo speaker, which is basically just a speaker. There's a crystal inside it. Essentially how it works is you apply a force to the crystal, and the crystal, based on that force, will vibrate a specific frequency, making a noise. So I basically send a square wave signal of 1200 hertz to the piezo speaker, and it makes it make a little noise. So the wire's connected here. It's connected to my piezo speaker. On the negative side, I have it going to the other side of that LED that I was talking about earlier. And then all that's connected down to the VSS, or my zero side, my negative side of the signal, just to complete the circuit. So the LED and the piezo speaker are kind of wired together. It's okay if you do that, because everything that's connected in a line is just all going to be connected, so it's not really a big deal. Yeah, so that's going to do that. I can make it play the frequency for you again. Let's reload the program in a second. Alright, here we go. Alright, and that's what it sounds like. So the frequency out signal is just going to give you a tone. The reason why you want to do that, though, every time that you write a program, is whenever your batteries are dying, then your robot's going to have the habit of restarting on its own. And so if you hear that tone, then you know, okay, I obviously started back at the very beginning of the program. A little, tangent. I think that for robotics, it's important for the robot to communicate to the user or the researcher or whoever is using it or working with it what's going on visibly and also audially, so that you, especially as a developer, don't really have to guess what state your robot is in or what your robot is thinking. So you have like the visual tones, you have did I say visual tones? I meant audio tones and visual signals. So, okay, anyways, yeah, that, and also the debug terminal whenever you got your little lifeline or nerve cord connected to it. Once you take out the cord, though, you won't be able to know what's going on in your debug terminal. That's why it's important for you to have signals that the user can understand, especially with like really rudimentary stuff and when you're just beginning. So, yeah, that's going to be the frequency out. Sorry about that tangent. Next thing you want to do is you want to program your do, which basically means, hey, robot, computer program, do this thing. Okay, so you want to do, sorry, I'm pointing with my hands. You want to do, and you also want to, at the very end, loop everything. This is all in one big loop. So essentially what's going to happen is the program is just going to start at the very beginning and then run through everything and then go back to the top again, and then run through everything and then go back to the top again. And this happens as fast as it can possibly do it. So, alright, first things first, I have my do, and then I want to do, sorry, I just turned it off. I wasn't thinking ahead. I'm going to reload the code again. So debug, freak out, do. Next thing it's going to do is every time it goes to this program, it's going to debug out, put the cursor at the 0, X and Y position, 0, 1, X, Y position, so basically the line right under the WISP navigation, which it honestly would have went there anyways because I have the carriage return. So really I could take that out and make my program just that much smaller to fit in more stuff. whenever you're writing code, that's one thing you want to look out for is redundant information or unnecessary information, because you're going to save a lot of program space in the very end, especially if you have something very sophisticated or very complicated. It's going to be big and chunky. You want to minimize the actual amount of characters that you input into your microcontroller. So anyways, 0, 1 position, it's going to say old 5, which is the old... I did it again. I hate it when I do that. I need to stop clicking. The old 5 value, which is going to be, like I said earlier, either a 1 or a 0. So old 5 value, as you can see right here, I want it to be a binary output. Binary 1, don't worry about the 1 at the end, just know that you need it. Old 5, so that variable that we declared earlier that was old 5, I want to output that just by itself. Next thing I want to do is go old 7, so just as a matter of convention, I put a space and a slash. I think that's a backslash, I always get confused. And then old 7, and that's going to output the value of whatever the old 7 was that the microcontroller read the last time it ran through the program sequence. That's going to be a binary output, and it's going to be old 7, the variable that we declared earlier. Next we want to debug is at the cursor XY position 0, 2, which is going to be directly underneath that. The counter. Now the counter comes into play down here. This is the AI subroutine for decision making. That's going to tell me whenever the robot is in a corner. Whenever there's an alternate pattern of whisker touching for 4 times or more, then it's going to realize it's in a corner and go to a subroutine for turning away. So we'll get to that in just a second. Anyways, the counter is going to count up each time that happens to know when it's 4 times or more. And I want to output that as a decimal value, so 0 through 9. And then it's the counter that we declared earlier. Right now it's 1, as you can see. Old 7 is 0, as you can see. And then old 5 is 1, as you can see. That was there, obviously, by design. And when you debug out your information that you put in, it's just going to make it that much easier for you to see what's going on, especially as you're developing the program. They don't really emphasize debugging out your information, I think, as much as they should, because you want to be able to see, like I said earlier, what your robot is thinking, so that you can tell, especially when you mess up, or when the robot is about to mess up, so you can write some code to counteract that. Okay, so that gets the debug out of the way. Just know that it's constantly refreshing. This is a little bit confusing, so I'm going to move on to the other portions of the program so that you can see a little bit better about what is going on. See, I'm really dumb. I should have just done that before. There you go again, not thinking ahead. Okay, so, right. The input 5 and input 7, like I mentioned earlier, is going to be connected to those switches for the whiskers. So, as you can see right here, whenever I press, that's going to be the left side. It's going to be the 7 switch. So it's going to make a tone, and then it's going to update the value that used to be in the 7 position. So now all of a sudden that's something new, or rather what it wasn't before. Old 5 is going to be the right-hand side, and as you can see, whenever I press the right-hand whisker, it's going to update the value to whatever it is. Okay, so yeah, and as you alternate patterns, the counter also goes up. And I'm at 3 right now, and once I get to 4, then it's going to go to the subroutine for backing up. So I'll just press the right-hand side to reset that, because the logical operation states that if the same side is pressed 2 times in a row, then the counter is going to go back to 1. So that's really important too, so that you absolutely know for certain that you're in a corner. Otherwise, you might get a little bit mixed up. Or you won't get mixed up, but your robot will get mixed up. And really, we care what he or her is thinking. He or she, not he or her. Is thinking rather than yourself once the cord is disconnected. So anyways, if input 5 and input 7 equals 0 at the same time, because remember they're going to be 1 all the time because the circuit is complete, input 5 and input 7 are the same at the same time, being 0, then your robot's going to know, obviously, that you hit a wall together. So whenever that happens, the subroutine is going to go for backing up and turning around. Turn left twice, which is basically do a 180. But yeah, first let's go through this line by line so you understand. So if input 5 and input 7 equals 0, then go to the next thing. Right here, okay, I made a comment about, basically a comment means it's not going to do anything. It's just like for the developer or for whoever you want to talk to or for yourself. I had a debug out for the old 5 and old 7 values every time that there was a change in input to the 7 or the 5 pins, but I realized that was kind of stupid and redundant because every single time my program initiates from the very beginning, at the beginning of the loop sequence, it's going to debug out that information anyways. So I was going to take it out, but I just wanted to leave it in there just to show you that sometimes if you have redundant information, you can just get rid of it. Because it's going to save you a whole lot of space allocation, which I'll get into in just a second. Anyways, so if it hits a wall straight on, it's going to make the input 5 and input 7 0 at the same time. So freak out, the same thing I did before with the beginning of the program, freak out on pin 9 for 200 milliseconds, 7,000 hertz, so on and so forth. So whenever I hit a wall, what am I going to do? Okay, because you got to think, every time something is hit, well, the robot is up against the wall, so it has to do something. So every time it hits both at the same time, it's going to back up. It's going to back up, and then it's going to turn left twice, which means it's going to turn completely around. And also on my debug terminal, it's going to show me skirt because I don't know. I just wanted it to say that, whatever. So yeah, as you can see down here, it goes skirt, and then pause for 2 seconds or 2,000 milliseconds. One thing I would recommend doing though is what's more important to you, your robot doing something if it runs into a wall, or it reporting back to you that something has happened. I think it's important for your robot to do something to get out of the situation, because it might get broken if it hits a wall, and it's more concerned about telling you it hit a wall than actually doing something about that. So really what I should have done is said go sub, back up, and turn left, and then done all that freak out stuff. But I kind of wanted the freak out stuff to happen first so that like I can hear it whenever the robot is operating, and then it does it, but then later it's concerned about outputting on the debug terminal what happened. So it's all up to you. But if this was going to be like for a military application or something that was more important, I would obviously want to have the go sub applications for doing something first, then reporting back to me what happened. So anyways, go sub, all that's going to do is take the program to whatever subroutine you have written. So go sub backup is going to go all the way down to the backup subroutine, which I already have pre-programmed in there. I'll get to that in a little bit. So yeah, it's going to back up, and it's going to turn left, and it's going to turn left again. And then it's going to report back to me with the cursor XY position 03, which is the third line of the debug terminal, skirt, so that I know what happened. And it's going to pause for 2 seconds so I have time to read it, because you know I'm the one who wants to know about that. So I'm going to leave it up on the screen for a little bit. I had it before where it wasn't 2 seconds, and you know it just like kind of flash and you might miss it. So you want to make sure that you program so that you can understand those communications. All right, so anyways, that's the first sequence of events that, you know, if that happens, then it's going to see that. And then else if, okay, else if is like, if this doesn't happen, then this other thing might happen. And if this happens, then I want you to do that. Okay, so else if 5 equals 0, and I believe 5 is the right-hand side. Yep. So, why are you not debugging out what's happening to you correctly? Very odd. I'm going to go ahead and reload the program. I don't know why that happened. Okay, so input 5. If that happens, then frequency out, I'm going to get a tone. high 10 is going to be a 1 signal to pin 10 of the microcontroller and then to the breadboard, and it's just going to light up that LED. So that doesn't do anything for my robot. That again is just communication for me. And then it's going to go sub, back up like I just showed you, and then it's going to turn right instead of turning left. It's going to back up and then turn this way. So okay. And then I send a, after that's done, I'm going to send a low 10 signal after it's done moving to turn the light off, the LED. Okay, else if input 7 is 0, then it's going to do the same thing, but I'm going to send a high signal or a 1 value to the 1 pin, back up and then turn left, because that means that I hit the opposite kind of corner. This is super important, okay, so know this or else you will not be able to get anything done. You have an else. If any of those things don't happen, then do this other thing. And this other thing is go forward, which is what you want your robot to do. If you don't do that, then it's not going to go anywhere. It's just going to wait for something to be pressed. And that's going to be really boring. And nothing may ever happen, especially if your robot's supposed to travel and it never travels anywhere. It's never going to hit anything, right? Kind of. I wouldn't speak in absolutes because you never know. Someone could kick you or something. Anyways, yeah, so else I'm going to debug out 0, 3 position, normal operation, which you can see right there. Okay, so that's going to end that whole if sequence. I have, this is kind of an odd way of doing it. I don't know if you may have noticed, but I have an if statement, and then else if, else if, else, and then end if. But up here in the decision-making code, I have a whole bunch of nested if statements. There may be a way to modify the code to do an if, else if. There probably is. I haven't messed with it yet, so I don't really know. But it may be a little bit more efficient doing it that way. So it's something that if I wanted to, I could experiment with, but I don't think I'm going to do that. Because I want to move on to the next sequence of sensor arrangements. So let's go look at what the different subroutines actually are so that it kind of makes more sense. Okay, so I have a forward pulse subroutine, which is going to move me forward. As you notice, the only one that really moves me forward is the else go forward if nothing else is occurring. So like it'll run through, you know, getting hit, and then if it's okay, I'm fine now, I'll just go forward, then it just goes. The big thing to understand about any programming language is that you start at the top and just run down the list. So if you understand that whenever something happens, you're going to go right back up to the top and then run through everything again, that gives you the basic understanding that you need to program anything, okay? Especially if it's in a loop. Okay, just know that something is going to go from top to bottom, like step 1, step 2, step 3, step 4. Okay, step 4 told me to do this, and I just did that, so now what do I do? Okay, I'm going to go right back to step 1. Step 1, step 2, step 3, step 4, so on and so forth. So anyways, the forward pulse subroutine that I have written is going to send a pulse out signal to the 13 servo motor. Oh god, what side is that? I have them taped off. 13 is going to be the left wheel. Okay, so 13 is going to be this side. It's going to send a waveform that is 824 microseconds times 2, because whatever you do these pulse out signals, it's not by 1, it's by 2. So every 1 is going to be 2 microseconds. So what, like 1648 microseconds? And then it's going to pause for 20 milliseconds. So just keep in mind that whenever you're doing your pulse out signals, that it's going to be in microseconds, and your pause signals are going to be in milliseconds. This is just how the servo motors are built. These ones in particular need microsecond signals and then a 20 millisecond pause between. But just that is going to keep it going forward. So it might look, if you're looking at the waveform, it'd be like bit, 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 bit. But since it's a continuous rotation servo motor, it's going to go, okay, and also, depending on whatever duration of time you have for the high side, or the high value or the 1 value of the waveform, is going to tell the servo motor how fast to spin, because it's getting like poked at a certain speed, I guess you could think of it that way. Anyways, turn left is going to be a little bit different. For the forward pulse subroutine, I don't have a pulse counter on it because I just want it to happen. Like, I want it to happen once, and then it to figure out if it wants to do it again. Because if I had it going for a specific period of time, I might have the robot going forward for like 2 seconds, but if there's a wall there, it's just going to keep going and crash into it and blow up. And I don't want that to happen. So I'd rather have it pulse just once and be like, did I hit a wall? Did I hit a wall? Did I hit a wall? Okay, I hit a wall. Now I need to go do this other thing. You know, so it's like, oh shit, okay, so I need to go hit it. Anyways, so yeah, the turn left though subroutine is written in such a way that it's just going to turn the robot at a specific angle, I guess you would say. I can't remember if I programmed this in 45 degrees or if I programmed it in 90 degrees. I think it's at 90 degrees because 2 turn left signals should make it go approximately 180 degrees. So anyways, 4 pulse count equals 0 to 15. Alright, basically the pulse counter, it's just going to count a number of times that something happens. So it's going to run through this specific set of code 15 times. So, and it's going to, it can either have an increment from 0 to 15, or decrement from 15 to 0. It's up to you. It really doesn't matter. It's going to do the same thing. Just know that it just counts however many times something happens. So pulse out once again for on pin 13 of the servo motor, 655 times 2 microseconds, and then pulse out 12, 655 times 2 microseconds, and then pause 20. The reason why these numbers look so different, and well, they're the same here, but different here, is that each servo motor, if you think about it, has to turn in a different direction, right? Like, this servo motor has to turn this way, and this servo motor has to turn basically the exact opposite way to go in the same direction, right? Like this one, in order for it to go forward, has to turn clockwise, and this one has to turn counterclockwise. So, big point to understand, right? So I think that 655 is going to be counterclockwise, so each of these are going to turn in the counterclockwise direction, which is going to turn my robot left. Okay, so as they're both going in the same, well, actually it'd be like this one will go this way and this one will go this way. I'll have to show you, like on the carpet or something, how it actually works out, because I'm not very good at explaining these types of things. So yeah, turn left, turn right is going to do the exact opposite. Back up is basically going to be going forward, but the opposite. So I have 824 times 2 microsecond pulses on 13 this time, and for backup I have it on 12 for 824 times 2 microseconds and pause 1. I also have one more subroutine written that is turn away, which is basically like back up and then turn left 3 times. And then all of these, sorry I forgot to mention, are going to go to the next, which means go up to the top again, and then return, which means go back to wherever the program told it to go somewhere. So I'm very sorry I forgot to mention that. I'm sure you saw it, but yeah, I neglected to mention it because I got so caught up in other stuff. Anyways, yeah, so to reiterate very quickly, once you go to the turn left subroutine, it's going to go 0 to 15 times through this whole thing. So to go through it once, next, it's going to go through it again, next, it's going to go through it again, so on and so forth until 15 times is done. And once that hits the 15, then it's going to return to whatever, whenever the program told it to go down there. So I have next return, let's say I was going to the 7 input, so the right hand side hit, and it says, okay, we'll back up first and then turn left. So then all of a sudden it's going to go back here because the subroutine has been completed, and then it's going to send a low signal to turn the LED off. So after everything is done, then the LED is going to turn off. Okay. Hope that's not too confusing. If it is, I'm really sorry. You can like contact me and I'll try and explain it a little bit better. So anyways, yeah, that's how that whole sequence works. And then I have the subroutine that tells me if I'm backed up into a corner or if I've hit a corner. Okay, so it's a set of nested if statements. And here we go. So I want you to notice something first so that this makes a little bit more sense, okay? I'm going to show you the whiskers, the touching, the LEDs, and I also would like you to pay attention to the old 5, old 7, the counters, and the output for whatever type of operation I'm in currently. Okay, so I hit the right-hand side. Okay, I hit the left-hand side. Alright. You see how they're going back and forth? Okay, so old 7 is the right-hand side. So you see, whenever I hit that, the microcontroller is going to see a 0 signal because the circuit got cut. Like there wasn't a continuous circuit anymore, and it notices that. So old 5 is the left-hand side. Whenever I press that, the LED is going to light up and it's going to make that tone, and old 5 all of a sudden is going to be 0. Now, how I'm going to know that I'm backed up in their corner is because there's going to be an alternating pattern of left and right whisker touches. So it's going to be like this. See the counter going up 2, 3. Okay. You would think, oh, I should be going to the backup subroutine or the turn away subroutine because I just hit it. Well, no, it's greater than 4, not equal to 4. You can set it to be equal to 4 if you would like. I just have it to go only if it's more than 4. So on the 5th one, it's going to make a turn, a tone. It's going to go to the subroutine for turning away, and then it's going to back up. Okay, so we'll go through the code for that, and hopefully you got what's going on. So, all right, the first thing I'm going to say is if input 7 and input 5 are not the same, then go to the very next line. But, all right, cool. So if old 7, which is right here, does not equal input 7, which means it got touched or it got moved, or there's a different value in there now than when it was before, and old 5 does not equal input 7, or sorry, old 5 does not equal input 5, then go to the next line of code. So old 7 right now is a 1. When I press it, it'll turn to 0. At the same time, though, I'm pretty sure I said this before, it's going to read whatever is on input 5. So even though 7 got touched, and last time maybe old 5 was 0, when old 7 turns to 0 itself, 1 didn't get touched, so the circuit was still complete. So it's going to say, okay, I'm going to log that. You know, this time it was a 1, the circuit was complete. So if old 7 and old 5 are different than they were previously, which is always going to happen, because that's the way that it works unless they're both touched at the same time, then I'm going to increment the counter 1. So my counter that was originally 1 is going to be counter plus 1. You can do basic math with most programming languages just by using the algebraic functions. So then old 7 is going to equal input 7. Old 5 is going to equal input 5. That's going to be really important because that's going to let the robot remember what it was previously so they can actually like act upon it. So whatever they are, whenever that happens, if this happens, then this happens, then it's going to change those values and it's going to remember them. Oh, there it goes again. All right, next line of code is going to say if the counter is greater than 4, which if you are watching down here, when the counter goes up greater than 4, then it's going to go to the very next thing. It's going to reset the counter back to 1, and it's going to output that that little song that you just heard on the same pin 9, for this amount of time, this frequency. It's going to send a high 10 signal, which turns on the LED like I described before, and a high 1 signal to the number 1 LED, or on the first pin, to turn it on. Go sub turn away is going to activate. So turn away subroutine is back up, turn left 3 times, and then return to wherever you were. Sorry, turn away is right here. Okay, so it's going to back up, turn left, turn left, turn left, return. Whenever you say go sub, you have a subroutine that goes to another subroutine, it's not really a big deal. So go sub, turn away, cool. What's underneath it? Go sub, back up. All right, I got to get it back up. So it goes back up, pulse count 0 to 25, pulse out, pause 20, next, goes 25 times, return. Okay, last time I was here, so now I need to go here. So go sub, turn left. It's going to go to the turn left subroutine. What's there? Oh, 4, pulse count 0 to 15. Okay, so do this 15 times. Pulse out, pause 20 milliseconds. Next, return. All right, and then turn. I was right here, so I go here. Oh, I need to go there again. You see, it's just like that. And then after all these subroutines are complete, you return back where you were originally, which is right here. And then after that's done, it's going to debug on the third line of the debug terminal. Turn away. So I'll show you. Watch the debug terminal. Watch the old 7s, the counters on this one. Okay, I got that tone, got the lights, and turn away is displayed on the screen for 2000 milliseconds, which is 2 seconds, for those of you that don't know the metric system. So anyways, yeah, then it's going to send a low signal to both of the LEDs. That's going to tell it to turn off. So low 10, low 1, it's going to send a 0 signal. It's going to basically cut off the lifeblood of the current going to those specific pins. And then it's going to end. So that's going to end that specific statement. So whenever you code nested if statements or nested anything statements, you want to make sure that you try and like line stuff up, because this if statement is going to end this if. Okay, this if statement is going to end on this end if. This if statement is going to end on this end if. You don't have to. It's just something for the programmer to see, to understand, so that it just makes it that much easier. So yeah, that's pretty much how that works. And then I don't know how I'm going to do this, but I'm going to put BMO on the ground so that you can see how the whole program works together. I don't know, I didn't really plan this out before, but I guess I do need to show you how it works. Yeah, Rock Band microphone, super ghetto. But anyways, okay, let me line it up. There's Tucker on the floor, sorry. Alright, so I have the power switch set to 1 right now, which is not going to power the servo motors. I need to set it to 2, and then watch what happens. It's going to start moving. Okay, as it's moving through the code, and it's not detecting any inputs, it's going to just tell it to go forward. Okay, you see how it's cycling through? It's just like, okay, forward, 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 I haven't touched anything, I haven't hit anything yet. Okay, and then I hit something on my right whisker, I'm going to turn around, and I'm going to freaking go the next direction. Alright, I hit 2 things at once, it's going to back up and turn. Okay, and then it's going to go forward. And you can see in there when the servo motors weren't turning, that's because I coded in those pauses in there for the debug terminal. The debug terminal outputs aren't going to do anything at this point because it's not plugged into the computer. So it's basically on its own. It's a little rover. Okay, so here's the alternating pattern whenever it's hit into a corner. I think the batteries are going dead. The servos sound pretty weak. Well, there you go. That was the alternate pattern subroutine. But I hit it 1 time, 2 times, 3 times, 4 times. Okay, the counter was in such a way that I didn't need to do it a 5th time. That's why I didn't have to hit it again. Like, it depends on what the old values were for 5 and 7. Anyway, so I'm going to put it on the ground. You can see. Yeah, the batteries are dying. Whenever I hit a left-hand wall, then it's going to turn away from that. If I hit a right-hand wall, it's going to turn away from it. Both at the same time, then it's going to turn around. And go forward. Also note, too, that whenever things are on the carpet, it's going to mess with your calibration a lot. Yeah, and you know what? I did change the pulse out so that it doesn't do a 90-degree turn. just because I just didn't want to do it like that. So this is going to be the corner subroutine. And there we go. So, oh. That was unintentional, but that was hilarious. Yeah, so anyways, that's how that works. So, next time I do another video, it's probably going to be just as long, just as boring. Hopefully you're into robots like I am. But it's going to have a different sensor set on the prototype area. So, thanks for watching, and hopefully you learned something, and, you know, hopefully you are interested in maybe doing it for yourself sometime in the future. So, all right, yeah, thank you so much. If you want to buy the book, it's this one right here. Parallax Incorporated does this. It's really super awesome. It's really easy. All you need to do is just follow the directions. Like, it's very simple, self-explanatory. So, okay, yeah, I guess I'll see you guys later. And if you have any questions, don't hesitate to contact me. All right, see ya.